These are stepper motors of the same type and same specification. The one in left seems to take discrete steps, but the one in right seems to run smoothly and continuously. The only difference between these two motors is the way they are driven.
Hey there, curious minds! Today we are diving into fantastic universe of stepper motors and incredible microstepping technique. Get ready to uncover how these motors make things move smoothly and silently. Even though driving a stepper motor is not a big deal, I will explain how to drive a stepper motor in detail. You just need a microcontroller and a driving circuit. But after you succeed in driving a stepper motor, you will face a big trouble. When you run the motor at high speed, everything seems to be okay, but at low speed, steps of motion looks like red hand of a clock, which is discrete and undesirable. In this video, I will explain stepper motors and their structure, different types of stepper motors, stepper motor characteristics, different methods to drive a stepper motor using microcontroller, and finally I will teach you the exact technique to make a stepper motor motion smoother at low speeds using pure microcontroller without Arduino libraries or additional or specific ICs or modules. So get ready to roll up your sleeves and join me in some hands-on learning. Stepper motors are one of the most popular and applicable electrical motors with specific features that make them suitable for particular applications. High torque at low speed and high accuracy make them usable in CNC machines, 3D printers or robotic arms, and open loop control make them easy to use. Before everything else, I'm gonna show you some stepper motors and discuss their specifications.
All of these are stepper motors. Stepper motors can be recognized by the number of wires coming out of them. Stepper motors usually have 4 wires like this car engine stepper motor, or 5 wires like this one, or even 6 wires like this one. However, there are exceptions. I have dealt with 3-wire stepper motors in the past. In addition, when you turn the shaft, you can feel its steps on your finger.
The first thing to discuss is the stepper motor type. You may have heard of many stepper motor categories: unipolar, bipolar, 4-wire, 5-wire, 6-wire stepper motors. I have to tell you that all of these are the same. Categorizing stepper motors into groups like unipolar or bipolar is done mostly based on how to drive them, not the stepper motor itself or its inner structure or its nature. Also, categorizing stepper motors by their wire count is not correct. You may ask how a 4-wire stepper motor can be same as a 6-wire stepper motor. Good question, I'm gonna explain.
Inside any ordinary stepper motor, there are some windings, actually 4 windings like these. Each of the windings has 2 ends. Then here you can see 8 ends. 1, 2, 3, 4, 5, 6, 7 and 8 ends. If you face a stepper motor that has 8 wires, it means that these winding ends are pulled out directly. If the stepper motor has 6 wires like this one, it means that the factory connects these 2 ends together and also these 2 ends together. Then they pulled out these 2 points along with A, B, C and D wires. Let's name these red points common wires and these A, B, C and D wires driving wires. If the stepper motor has 5 wires like this one, then windings are wired like this, and this point is pulled out along with driving wires. Points A, B, C, and D. I'm going to call this wire as a common wire. And finally, if the motor has 4 wires like this car engine stepper motor, inner wiring is something like this and only points A, B, C and D are pulled out. Remember, I'm talking about ordinary stepper motors. I mean, maybe there are other stepper motors with other structures. You have to be careful.
At this stage, I know you are thinking about unipolar and bipolar categories. You may ask which one of these is unipolar and which one is bipolar. I'm sorry to let you know that all of these are unipolar and bipolar at the same time. It is weird, right? This is a common mistake to affix a unipolar or bipolar label to a stepper motor. Actually, unipolar or bipolar is a label for the method by which we are driving the stepper motor, not the stepper motor itself.
If the direction of current in all windings inside the stepper motor does not change at all, we call the driving method unipolar, and if the direction of current changes, we call it bipolar. In this structure, we have connected common wires to source voltage, so you can drive the motor by syncing each of A, B, C or D wires, and it is obvious that the current will always flow from common wires to A, B, C and D wires. In this structure, it is not possible for current to flow from A, B, C or D wires to common wires, so this driver is a unipolar driver. But this structure is different. This is a 4-wire stepper motor or a 6-wire stepper motor, which common wires are left in the air. In this structure, the driver is able to apply either source or ground voltages to each of A, B, C or D wires. So the direction of current can be changed in driving wires. For example, if the driver applies source voltage to A and ground voltage to B, then the current will flow from A to B. But if the driver applies source voltage to B and ground voltage to A, then the current will flow from B to A. It means the direction of the current can be changed. So this method is a unipolar method.
In short, a unipolar driver needs a common wire hooked up to ground or source voltage along with driving wires to drive a stepper motor, but a bipolar driver can drive the stepper motor using only driving wires and doesn't need a common wire. So 5 and 6 wire stepper motors can be driven using either unipolar or bipolar drivers, and a 4 wire stepper motor is forced to be driven exclusively using a bipolar driver due to absence of common wire. Note that the direction of current in a stepper motor inner windings has nothing to do with the direction of motion of motor shaft.
To drive a stepper motor, I mean to make the shaft turn clockwise or counterclockwise at a desired speed, we need to apply proper voltages to these wires at right time. If you look at the label on the motor, you can find the basic properties of the motor. For example, on the 6-wire stepper motor, those details are written here. According to the information provided here on this label, we have to apply 3.2 volt or 0 volt to these wires to control the speed and direction of the shaft. I'm going to call this 3.2 volt motor voltage. To drive this stepper motor, we need to hook up these 2 wires to motor voltage. These are common wires, and apply 0 volts to these wires periodically. These are A, B, C and D wires. This is the step table of a full-wave unipolar stepper motor driver. Look at this table. In first state, 0 volt is applied to point A and other points are left in the air. They are not connected. In second state, point B is grounded and other points are left in the air. In third state, point C is grounded, and in last state, 0 volt is applied to point D. To turn the shaft clockwise, we need to apply these states in this order. 1, 2, 3, 4, 1, 2, 3, 4 periodically to the motor. And to turn the shaft counterclockwise, we have to apply these states in reverse order to motor, like 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1 repetitively. The speed of rotation depends on how fast you go from state to state. For example, if you go like this, 1, 2, 3, 4, 1, 2, 3, 4, this will result in slow rotation of the shaft. And if you go like this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, this will result in fast rotation of the shaft.
Each state is equal to one step, and each step is equal to 1.8 degree. You may ask, why is each step 1.8 degree? This is one of stepper motor's characteristics. It is written on the motor here. It means that we need to apply 200 steps to the motor to make the shaft turn one complete revolution. I mean, to make the shaft turn one complete revolution, we need to go through this table 50 times. You may ask, how do you make these state sequences on a circuit? I'm gonna answer.
There are several solutions, but one of the most precise and easy solutions is to use a microcontroller. GPIO pins of a microcontroller can generate this sequence of states easily, but they can't deliver much current, so we can't hook up the stepper motor directly to the microcontroller. Look here. This stepper motor draws about 1.2 amperes, while the output pins on this microcontroller GPIO can provide only few milliamps. To drive this motor using this microcontroller, we need an intermediate circuit which is called a driver circuit.
There are two main approaches for making driver circuits to drive a stepper motor: using transistors or driver ICs like L298, L6203, etc. Both transistors and driver ICs can be used to make either unipolar or bipolar drivers. Choosing right driver circuit and method is mostly depends on the application and the project you are working on. In this video, I'm gonna use transistors to make driver circuit, and I will make a unipolar driver out of transistors. Note that to make a bipolar driver out of transistors, you have to use a transistor structure called H-bridge.
These are TIP122 Darlington pair transistors that can switch loads up to 5 amperes, and these LEDs are here for indicating the signal on microcontroller output terminals. You also need to connect MOSI, MISO, STK and reset terminals on microcontroller to corresponding pins on the programmer. I have used 2 pins here as input to control the speed of the stepper motor. Let's set up the circuit and test it. Look here, the motor is running. To make its movement more visible, I'm gonna stick this PCB to the shaft. With these 2 tactile switches, I am able to control the speed and direction of the motor.
You may set up the exact same circuit with the exact same program, but it doesn't work for you. In such a case, it is likely that you didn't connect the driving wires in right order. In this video, I assume that the driving wires are in this order, A to D, but in real-world stepper motors, the order of driving wires may vary. For example, the order of driving wires on your stepper motor maybe are in this order, or this one, or this one. You can find the right driving wire order by trial and error or referring to the datasheet.
Look here, at high speeds the rotation of motor is almost smooth, but in low speeds discrete steps are clearly visible and completely sensible. This is not acceptable in most applications. What we can do?
There is a technique to make low speed steps smooth. It is called microstepping. This technique is to divide each single step into desired number of sub-steps, 2, 4, 8, 16 or even more. How to do that? Let's see.
Dividing a single step into two sub-steps is super easy. If you are driving the motor using a unipolar method like what we are doing in this video, you only need to expand this table into this one. It is very clear. These states between main states, I mean this one, this one, this one, and this one, are combination of the main states. You see, in this state, winding A is on and winding B is off. And in this state, the winding B is on and winding A is off. But in this intermediate state, actually these two are on at the same time and create a half state. To do this, we just need to alter the code. The driving circuit is okay. Let's try this. This is running at full step, and now it is running on half state. You can see the difference.
This method is called half step or half wave driving, and now the steps are a bit softer than before, but the steps are still rough and not completely smooth. What we can do? Yes, that's right. The answer is simple, to add more sub-steps. But implementing this simple answer is not as simple as you expect. We have to make some fundamental changes in the code to make us able to control the force produced by each winding. I know it is getting confusing. Let me explain.
This is the stepper motor and this one is the shaft. Suppose that here is the current step, say point A, and here is the next step, say point B. I'm gonna zoom this area here to make it more visible. In full wave driving, going from A to B was done at once and immediately. In the half wave method, the shaft would come here to this point in the first half step and go here in the next half step. But in microstepping, we intend to hold the shaft in intermediate points almost everywhere between A and B. To do that, we need to apply proper voltage to winding wires to limit the current. Here is the point X. The distance between point X and point A is D, and the distance between point X and point B is 7 times D. Suppose that you want to hold the shaft on point X, then you have to apply 7/8 of motor voltage to winding A and 1/8 of the motor voltage to winding B.
The theory is really simple, but there are two main problems in real-world projects. The first problem is to find the best and efficient method to control the voltage or current on each winding wire. There are a lot of solutions, for example PWM, which is very simple and handy, and it is controlling the current or voltage by increasing or decreasing duty cycle. The second problem is so weird and will appear after implementation implementing the PWM. Let's get started.
This is a table from previous sections. Let's look at it again. State 1 is where winding A is active and all other windings are inactive. State 2 is where winding B is active and all other windings are inactive. State 3, winding C is active. State 4, winding D. An active winding means that the PWM on that winding is 100%, and inactive winding means that the PWM on that winding is 0%. So if you want to go from state 1 to state 2 in microstepping, you have to decrease the PWM on winding A to 0 gradually. In the same time, increase the PWM on winding B from 0 to 100% in the same time. When the PWM on winding B reaches to 100%, it means that the step is completed and you have to take the next step. Next step is to go from state 2 to state 3, where the winding C is active. So the similar thing will happen here. You have to decrease the PWM on winding B from 100% to 0% gradually, and in the same time you have to increase the PWM on winding C from 0 to 100% in the same time, like this. When the PWM on winding C reaches to 100%, it means that this step is completed and you have to take the next step. Next step is to go from state 3 to state 4. You can repeat this process to take more and more steps. I'm going to write the PWM based driving program and test the new driver. The result is not what we expected.
The motor may vibrate like this, and this is normal. It is happening because of heterogeneity between two PWM pulses on neighboring windings. I know you thought that this was the second problem I already mentioned, but no, this vibration can be simply fixed by using 4 capacitors on transistor outputs. Actually, these capacitors are converting PWM pulses into analog voltages.
Like this. Actually, these capacitors aggregate the PWM on-time voltage and form an analog voltage. Look at the shaft. The vibration and the noise is gone and the movement of the shaft is a bit softer, but still it is not what I expected.
After applying microstepping, the movement of the shaft was not what I expected. This is the second problem that I mentioned earlier. This is the movement of the shaft before applying microstepping, and this is the movement of the shaft after applying microstepping. This is a bit softer than before, but it is still unacceptable. What is the problem?
This is happening because the force produced by the winding is not linear. I mean the amount of force the winding produces at 80% duty cycle is not 4 times bigger than the force produced by the same winding at 20% duty cycle. They are extremely different, and this fact causes high stiffness for the shaft to the main step points.
Solving this problem is not very difficult. You have to select substep points non-linearly. I mean the distance between two substep points should not be equal. For example, I found these points for my stepper motor by trial and error, and I am using these instead of these, which are selected linearly by equal distance of 32. These points are great, although you can find better ones. Last thing to mention is the range of these numbers. You may expect these numbers to be between 0 and 100, but they are not. They are between 0 and 255. The reason is the resolution of PWM on microcontroller, which is 256. This is why the minimum step point in these numbers is 0 and the maximum step point is 255. So that's it, that's done. Let's test these numbers and see the result.
It looks great and now it is working just fine.
The method that is implemented in this video is not the only one to implement microstepping method, and there are many other methods you can learn about them. By the way, I wrote the code in Atmel Studio for 80MB AVR microcontroller, and all the code for all three methods of driving stepper motors are available there. There is a link to that code in description. So my friend, I hope you enjoyed this video and learned something new. Thanks for watching. If you find this video helpful, please give me a thumbs up, and if you like this video, make sure to subscribe for more.